The rejected formula sat in a filing cabinet for 3 months before anyone noticed it could win the war. Professor Louis Fieser's hands trembled as he held the declassified rejection letter from the National Defense Research Committee, dated November 14th, 1941. Insufficient adhesive properties for military application. It read, "Recommend discontinuation of research." 3 weeks later, Pearl Harbor burned, and suddenly, insufficient wasn't good enough anymore. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. December 7th, 1941, changed everything. As Japanese Zeros carved through American battleships at Pearl Harbor, military strategists scrambled to understand what they were facing. This wasn't the war they'd planned for. The enemy they'd underestimated had just demonstrated tactical brilliance, technological sophistication, and an appetite for fortification that would redefine defensive warfare. Within 72 hours of the attack, the War Department reopened every weapons research file that had been shelved, dismissed, or deprioritized. Among them, buried under reports on poison gas alternatives and explosive compound variations, was Fieser's rejected incendiary research. The same mixture that had been deemed too unstable, too viscous, too unpredictable, was about to become America's most requested weapon in the Pacific theater. Louis Frederick Fieser was not a warrior. Born on April 7, 1899 in Columbus, Ohio, he had dedicated his life to healing, not killing. His research into vitamin K synthesis had advanced blood coagulation treatments. His work on anti-malarial drugs promised to save thousands of lives in tropical climates. He was an organic chemist, a Harvard professor, a man of science who believed knowledge should serve humanity's betterment. When war broke out in Europe, Fieser had joined countless other American scientists in signing declarations opposing chemical warfare development. He had seen the photographs from the First World War, the soldiers blinded by mustard gas, the lungs scarred by chlorine. He wanted no part in creating such horrors, but Pearl Harbor didn't ask for volunteers. It demanded everyone's service. The call came on December 10th, 1941, just 3 days after the attack. Dr. James Conant, president of Harvard and chairman of the National Defense Research Committee, summoned Fieser to his office. The meeting lasted 17 minutes. Conant didn't offer pleasantries or philosophical discussions. He placed photographs on his desk. Aerial reconnaissance images from the Pacific showing Japanese fortifications on island after island, concrete bunkers, underground networks, cave systems that could house entire battalions. "Standard explosives bounce off," Conant said, tapping one photograph. "Artillery shells create surface damage but don't penetrate. We need something that flows, something that seeks out the enemy in places bombs can't reach. Your rejected formula, Louis. Tell me about it." Fieser had been experimenting with thickened petroleum since 1939, initially researching synthetic rubber alternatives as war in Europe disrupted natural rubber supplies from Southeast Asia. During those experiments, he'd discovered that certain aluminum soap compounds, specifically aluminum naphthenate and aluminum palmitate, could transform liquid gasoline into a gel with remarkable properties. The mixture achieved a consistency similar to applesauce when first prepared, then thickened to something resembling rubber. More importantly, it maintained fluidity when projected under pressure, but adhered tenaciously to whatever surface it contacted. When ignited, it didn't explode like conventional fuel. It clung and burned with temperatures ranging from 800 to 1200 degrees Celsius, 6 times hotter than thermite incendiary compounds then in use. The National Defense Research Committee had reviewed Fieser's initial findings in late 1941, shortly before Pearl Harbor. Their rejection hadn't been entirely dismissive. The chemistry was sound, they acknowledged. The thermal properties were impressive, but the military applications weren't immediately obvious. America wasn't at war yet. Research funding was limited. Priority went to defensive technologies, radar improvements, aircraft development. An experimental incendiary gel that required specific mixing ratios and careful handling seemed impractical for battlefield deployment. Besides, What would they use it against? The committee filed the research away and moved on to more pressing matters. Then everything changed. Conant reopened the file because the Pacific War demanded new thinking. Japanese defensive doctrine had evolved rapidly during their conquest of China and Southeast Asia. They had learned that fortified positions, properly constructed and fanatically defended, could withstand overwhelming firepower. The Battle of Shanghai in 1937 had demonstrated this principle. Chinese forces, outnumbered and outgunned, had held fortified positions for 3 months against Japanese assault. The lesson wasn't lost on Japanese military planners. If fortifications could delay a superior enemy, they could potentially defeat an invasion force. By 1941, Japan had transformed defensive warfare into an art form. Every island they controlled became a fortress. Engineers excavated caves through volcanic rock. Construction battalions poured concrete bunkers with walls 3 feet thick. Underground passages connected defensive positions, allowing troops to move unseen. Ventilation shafts provided air to subterranean garrisons. Water cisterns and ammunition dumps were carved into solid rock. These weren't simple trenches or earthworks. These were engineered fortresses designed to withstand naval bombardment and aerial attack. American military doctrine had no answer for this. The United States had spent the 1920s and 1930s preparing for a different war, one where battles would be decided by maneuver and firepower superiority. The concept of systematically reducing fortified positions one by one across thousands of miles of Pacific islands hadn't factored into strategic planning. Standard high-explosive bombs, effective against surface structures and troop concentrations, proved nearly useless against underground fortifications. A 500-pound bomb might crater the earth above a cave system, but leave the defenders untouched below. Naval gunfire, devastating against ships and coastal installations, couldn't reach reverse slope positions or penetrate deep into hillsides. Artillery bombardment could suppress surface defenders but couldn't eliminate troops sheltered in concrete-reinforced caves. The Japanese had effectively neutralized America's technological advantages. Superior air power meant nothing if bombs couldn't reach the target. Naval superiority was irrelevant if shells bounced off fortifications. Industrial capacity couldn't help if weapons didn't work. Something new was needed. Something that could flow into caves, penetrate bunkers, reach defenders in places conventional weapons couldn't touch. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Fieser returned to his laboratory at Harvard with renewed purpose. The rejection that had stung 3 months earlier now seemed irrelevant. His country was at war. American soldiers and Marines would soon be dying trying to overcome Japanese fortifications. If his research could help, he would pursue it regardless of previous setbacks. He began by revisiting his experimental notes from 1939 and 1940. The basic chemistry was sound. Aluminum naphthenate and aluminum palmitate, when combined with gasoline in specific ratios, created a gel that maintained stability during storage, but flowed when agitated. The challenge was optimizing the formula for military application. It needed to be stable enough to ship across oceans, simple enough for field troops to prepare, and effective enough to justify the logistical burden of deploying a new weapon system. The work consumed him. Fieser spent January and February of 1942 conducting trial after trial, adjusting ratios, testing different aluminum soap variations, measuring combustion temperatures, timing burn durations. His laboratory in the Converse building basement became a workshop of controlled destruction. Each day brought incremental improvements. A slightly different aluminum compound ratio produced better adhesion. Adjusting the mixing procedure created more consistent gel formation. Testing various ignition methods revealed optimal deployment techniques. By Valentine's Day, 1942, Fieser believed he had perfected the formula. The moment of truth came at 2:37 in the afternoon. He prepared a small sample, exactly following the refined procedure. The aluminum soaps dissolved into the gasoline, and the mixture thickened. He noted in his laboratory journal that the consistency resembled applesauce initially, then continued thickening until it achieved a rubber-like quality. Perfect. He set the sample aside and reached for a match. The flame didn't behave like burning gasoline. It didn't flash or explode. It caught, spread slowly, and clung to the container. The gel continued burning steadily, impossibly hot, refusing to be easily extinguished. Fieser tried water. The burning gel floated and continued combusting. He tried smothering it. The gel's own oxygen content sustained combustion. He tried scraping it away. The gel adhered so tenaciously that removal was nearly impossible while burning. This was it. This was what the military needed. A weapon that couldn't be dodged, couldn't be blocked, couldn't be hidden from. Something that would reach into the deepest cave and burn until nothing remained. Fieser picked up the secure telephone and called Washington. Within hours, military chemists were reviewing his notes. Within days, field testing was scheduled. Within weeks, production planning began. The weapon that had been rejected as impractical was about to change the Pacific War. But first, it needed a name. The military bureaucracy insisted on official nomenclature. Scientists working on the project began referring to it by its chemical components, naphthenate and palmitate, shortened to napalm. The name stuck. It sounded technical, clinical, detached from what it actually did. Perhaps that was intentional. Perhaps it was easier to deploy a weapon called napalm than one called jellied fire or clinging death. Language has always been warfare's first casualty, and naming conventions often serve to distance creators from consequences. Fieser, however, understood exactly what he had created. His laboratory notes from February 1942 contain a passage rarely quoted in official histories. "This compound will save American lives by making enemy fortifications untenable," he wrote. "I pray it is used wisely, and that when this war ends, such weapons become unnecessary." It was the hope of a scientist who believed technology could be controlled, that moral considerations would limit application, that humanity would somehow emerge from global conflict with principles intact. Events would prove him tragically optimistic. The first field test was scheduled for July 4, 1942, not at some remote military proving ground but on Harvard's own soccer field, the open space between the business school and the stadium. The location seemed absurdly mundane for testing a weapon that would reshape warfare. But practicality demanded proximity to Fieser's laboratory. Time was critical. Every day delayed was another day. American forces would face Japanese fortifications without adequate weapons. The test was simple in concept. Demonstrate that the napalm mixture could be deployed, ignited, and sustained under field conditions. Show that it performed as laboratory results suggested. Prove it was worth the investment of resources, production capacity, and logistical complexity required to field a new weapon system. Cambridge Fire Department representatives arrived early, suspicious and concerned. Tennis players on nearby courts continued their games, unaware that history was about to erupt on a field they passed daily. Fieser and his team prepared the demonstration carefully. They constructed a shallow pool to simulate water-filled environments where conventional incendiaries failed. They positioned 45 pounds of napalm mixture, a substantial quantity that would provide clear results. They briefed observers on what to expect, though in truth, none of them fully understood what was about to happen. At precisely 1000 hours, Fieser nodded to his assistant. The white phosphorus igniter triggered. For a fraction of a second, nothing seemed to happen. Then, the napalm erupted. Flaming globs of gel shot into the air, some arcing 30 feet before splashing down. Where they landed, fire spread. The gel stuck to everything it touched, burning with intense heat that observers could feel from 50 yards away. Most dramatically, chunks of burning gel fell into the water pool and continued combusting. They floated on the surface, flames dancing above the waterline, defying every intuition about how fire should behave. The tennis players stopped mid-serve, stunned. One dropped his racket and ran. Others stood frozen, watching flame dance on water, unable to process what they were witnessing. The fire department representatives, professionals who'd seen every type of fire, stood silent. This was something new, something unnatural, something terrifying. The test lasted 6 minutes, the time required for the napalm samples to fully combust. When it ended, the soccer field bore scorch marks that would remain visible for weeks. The water pool was blackened but intact. The napalm had performed exactly as Fieser predicted. It stuck, it burned intensely, it couldn't be easily extinguished, and it maintained combustion even in adverse conditions. The military observers began taking notes immediately. Deployment methods, ignition systems, storage requirements, transportation considerations. Within hours, they were drafting production orders. The chemistry of destruction had proven itself viable. Now came the industrial challenge of mass production. The transformation from laboratory curiosity to battlefield weapon required an industrial mobilization that rivaled anything America had attempted. Within days of the Harvard soccer field demonstration, the War Production Board classified napalm production as highest priority. Factories across the nation received orders to retool assembly lines. Chemical plants that had been producing peacetime products suddenly found themselves manufacturing aluminum soaps and specialized mixing equipment. The scale of the undertaking revealed something fundamental about American power during the Second World War. It wasn't just that the United States could produce weapons in vast quantities. It was that the entire industrial infrastructure could pivot almost overnight from civilian production to military necessity. This flexibility, this capacity to transform purpose at national scale, would prove as decisive as any tactical innovation. Dow Chemical Corporation received the primary production contract in March 1942. Their facility in Midland, Michigan, had been producing chemical compounds for agriculture and consumer products. Within 60 days, entire sections of the plant had been converted to napalm component production. Engineers designed specialized mixing equipment that could combine gasoline and aluminum soaps in precise ratios without creating safety hazards. Workers learned new procedures, new safety protocols, new quality control standards. The compound had to meet exacting specifications: too thin, and it wouldn't adhere properly; too thick, and it couldn't be deployed from aircraft or ground equipment. Temperature sensitivity was critical. The mixture had to remain stable in tropical heat and Arctic cold. It had to survive weeks aboard transport ships crossing the Pacific. It had to function reliably whether deployed at sea level or high altitude. Every batch underwent rigorous testing before approval for shipment. The margin for error was non-existent. A faulty batch could mean American troops facing fortified positions without the one weapon that could save them. Neverex Products in Massachusetts received secondary production contracts. Their facility had manufactured industrial lubricants and specialty chemicals. By April 1942, they had developed a brown, dry powder version of napalm that looked deceptively harmless, like cocoa powder or instant coffee. This innovation solved a critical logistical problem. Shipping liquid gasoline across oceans was dangerous and space inefficient. But shipping powder was safe, compact, and simple. Troops in the field could mix the powder with local gasoline supplies, creating napalm on demand. The tactical implications were profound. Instead of requiring dedicated supply chains for a specialized fuel mixture, napalm could be produced anywhere gasoline was available. Forward bases, island airstrips, even ships at sea could maintain napalm capabilities without massive logistical support. This flexibility meant the weapon could be deployed throughout the Pacific theater without straining already overtaxed supply networks. Production numbers climbed with astonishing speed. In mid-1942, American factories produced 500,000 pounds of napalm components monthly. By early 1943, that figure had reached several million pounds. By 1944, monthly production exceeded 8 million pounds. The numbers represented more than industrial capacity. They represented national will, the collective determination to provide American fighting men with every possible advantage. Factory workers who mixed aluminum soaps and gasoline powder understood they were producing something consequential, even if they didn't fully grasp the weapon's battlefield application. They worked extra shifts, met impossible quotas, took pride in production numbers that kept climbing. Their work wasn't glamorous. It didn't make headlines, but it would save countless American lives and help end the war more quickly. That knowledge drove them through exhaustion and repetitive labor. They were doing their part, just as surely, as the soldiers, sailors, and Marines who would deploy their product against Japanese fortifications. The Chemical Warfare Service, responsible for coordinating development and deployment of specialized weapons, established dedicated units to handle napalm operations. These weren't combat troops in the traditional sense. They were specialists who understood the weapon's unique properties and requirements, storage specialists who ensured proper temperature control and safety procedures, transportation experts who coordinated shipment across vast Pacific distances, training personnel who taught combat troops how to deploy the weapon effectively and safely. The organization grew from a handful of officers and enlisted men in early 1942 to thousands by 1944. They established bases throughout the Pacific, stockpiling napalm components at forward positions. They coordinated with Navy construction battalions, the famous Seabees, to build specialized storage facilities on newly captured islands. They worked with Army Air Force planners to develop aerial deployment tactics. Every aspect of getting this new weapon from factory to battlefield required coordination, innovation, and relentless attention to detail. Meanwhile, weaponization proceeded in parallel with production. The napalm compound was extraordinarily effective, but it needed delivery systems optimized for different tactical situations. The M69 incendiary bomb became the primary aerial weapon. Each bomb weighed 6.2 pounds and contained jellied gasoline that would spray across a 15-foot diameter when the casing burst. The design was elegantly simple. A hexagonal steel tube contained the napalm. A white phosphorus igniter at the nose ensured reliable ignition. Stabilizing fins provided accuracy during descent. When dropped from aircraft, the M69 would tumble end over end, spreading its burning payload across a wide area. 38 M69 bombs were clustered together in an E-46 cluster bomb assembly. This larger weapon could be carried by fighter bombers or heavy bombers. When released, the cluster would descend to approximately 2,000 feet, then explosively separate, scattering the individual incendiary bombs across a target zone. A single cluster could saturate an area the size of a football field with burning gel. Multiple clusters could create firestorms that consumed everything within reach. Ground forces required different solutions. The M2 flamethrower became the primary infantry weapon. It consisted of 2 cylindrical fuel tanks, a nitrogen pressure cylinder, a hose assembly, and an ignition system. When fully loaded, the complete unit weighed 70 pounds, a crushing burden for infantry soldiers already carrying weapons, ammunition, water, and equipment. The operator could project a stream of burning napalm up to 40 yards, though effective range was typically half that distance. The weapon was devastatingly effective against fortified positions. A single burst through a bunker firing slit could clear an entire defensive position. The superheated gel would flow through the fortification's interior, igniting everything combustible and consuming oxygen so rapidly that defenders often suffocated before the flames reached them. But flamethrower operators paid a terrible price for their effectiveness. They were priority targets for enemy fire. The fuel tanks on their backs were vulnerable to bullets and shrapnel. If penetrated, the tanks could explode or burn, killing the operator instantly. Casualty rates among flamethrower troops exceeded 90% once they revealed their position by firing. These were men who volunteered knowing the odds, understanding they likely wouldn't survive the war, accepting that burden because their weapons saved other American lives. The final piece of the tactical puzzle came from an unexpected source. Navy construction battalions, the Seabees, were tasked with modifying Sherman tanks to carry flamethrowers. These units had been created to build airfields, roads, and facilities on captured islands. Their personnel were older than typical combat troops, many with civilian construction experience. They were engineers and welders, electricians and mechanics. They weren't supposed to be weapons innovators, but necessity drove innovation, and the Seabees proved remarkably creative. The concept was straightforward. Replace a Sherman tank's main gun with a flamethrower projector, install fuel tanks in the hull, add pressure systems and ignition equipment. The result would be a mobile flamethrower with armor protection for the crew and fuel supply. Implementation proved far more complex. The flamethrower had to withstand the stress of tank operations, rough terrain, and combat conditions. Fuel systems had to be isolated from the crew compartment to prevent catastrophic explosions if penetrated. Pressure systems had to function reliably despite vibration and shock. Ignition systems had to work in rain, mud, and tropical humidity. CB units worked around the clock developing prototypes. Electricians mate Joseph Klein and shipfitter J.T. Patterson led the initial design team. They tested dozens of configurations, learning through trial and error what worked and what failed catastrophically. Early prototypes had fuel lines that cracked under stress, pressure systems that leaked, ignition systems that failed in damp conditions. Each failure was analyzed, corrected, and retested. By mid-1943, they had developed a reliable system designated the CBH-1 flamethrower. Mounted in a Sherman tank, it could project napalm streams up to 150 yards with devastating accuracy. The tanks were nicknamed Zippos by Marines who saw them in action, after the popular cigarette lighter. The name captured both the weapon's function and the grim humor of men facing combat. Like a Zippo lighter, the flame tanks ignited reliably and burned intensely. Unlike a Zippo, they consumed entire fortifications instead of cigarettes. Production of flame tanks began in early 1944. Standard Sherman tanks were diverted from assembly lines and sent to modification facilities where CB teams installed flamethrower systems. The work required precision and skill. Welding had to be perfect to prevent fuel leaks. Electrical systems had to be isolated and protected. Armor modifications had to maintain the tank's structural integrity. Each conversion took approximately 3 weeks and required specialized tools and trained personnel. By mid-1944, flame tank production had reached a steady pace of dozens per month. These vehicles were assigned to Marine Corps tank battalions throughout the Pacific. Each battalion typically received 8 to 12 flame tanks to supplement their conventional gun tanks. The flame tanks would lead assaults on fortified positions, neutralizing bunkers and caves, while gun tanks provided covering fire against enemy counterattacks. The tactical synergy was perfect. Flame tanks eliminated fortifications. Gun tanks protected flame tanks from anti-tank weapons. Infantry secured the ground cleared by both. Training for flame tank operations became a specialized school. Crews had to learn not just how to operate the flamethrower system, but when to use it most effectively. Range estimation was critical. Too far away, and the napalm stream would dissipate harmlessly. Too close, and the tank risked being enveloped in its own flames if wind shifted. Target selection required understanding Japanese defensive construction. Bunkers built into hillsides often had multiple firing ports. The operator had to identify the main entrance and ventilation shafts to maximize napalm penetration. Cave systems required different techniques. A single burst into the cave mouth might not suffice if the passage curved or branched. Multiple applications from different angles ensured complete coverage. Coordination with infantry was essential. Flame tanks were vulnerable to Japanese soldiers armed with satchel charges and magnetic mines. Infantry had to clear enemy anti-tank teams before flame tanks could close on fortifications. Suppressive fire from conventional weapons kept defenders focused away from flame tank approach routes. Timing was everything. Launch the flame attack too early, and defenders had time to react. Too late, and infantry assault forces suffered unnecessary casualties. The first combat deployment of napalm in the Pacific Theater occurred in July 1944 during the Battle of Tinian in the Mariana Islands chain. The target was a heavily fortified island that Japanese forces had spent months preparing for defense. Intelligence estimated approximately 9,000 Japanese troops had excavated extensive cave networks and concrete fortifications. Conventional bombardment had proven largely ineffective. Naval gunfire had cratered the surface, but left underground defences intact. Aerial bombing had achieved similar limited results. The assault forces needed something that could reach into those caves and bunkers. They needed napalm. The first strikes came from Army Air Force fighter bombers, carrying cluster munitions loaded with M69 incendiary bombs. The aircraft approached at medium altitude to avoid concentrated anti-aircraft fire, then dove to release altitude. The clusters separated on schedule, scattering individual incendiary bombs across Japanese defensive positions. What happened next stunned observers watching from nearby Saipan. Instead of discrete explosion points, entire hillsides erupted in flame. The napalm spread in sheets of fire that flowed into cave openings and bunker entrances. The burning gel penetrated defensive works that had resisted weeks of conventional bombardment. Japanese soldiers emerged from positions that had seemed impregnable, their uniforms and equipment aflame, desperate to escape the inferno consuming their fortifications. Marine observers recording the attack noted something profound. For the first time in the Pacific War, Japanese defenders were abandoning fortified positions en masse before American troops even began ground assault. The psychological impact was as devastating as the physical destruction. Marines who had spent months fighting for every yard against fanatical resistance suddenly watched enemy soldiers flee in panic. The weapon that had been developed to overcome physical fortifications was breaking something equally important: the conviction that defensive positions offered protection, that determination could overcome firepower, that willpower could defeat technology. Napalm was teaching a brutal lesson. In modern warfare, there was nowhere to hide. The tactical revolution became undeniable within 72 hours of that first napalm strike on Tinian. What had required days or weeks of brutal close-quarters combat could now be accomplished in hours. Japanese defensive positions that had been considered nearly impregnable were systematically eliminated by coordinated napalm attacks. The island fell on August 1st, 1944, far faster than military planners had projected. Of the 9,000 Japanese defenders, only 313 survived to be captured. The vast majority had died in their fortifications, consumed by flames they couldn't escape, or suffocated when napalm consumed the oxygen in sealed chambers. The statistics were compelling enough that every Marine division in the Pacific immediately requested priority allocation of napalm weapons. The success sparked a fundamental reassessment of Pacific War strategy. Islands that had been bypassed as too heavily fortified suddenly became viable targets. Invasion timelines were accelerated. Casualty projections were revised downward. The weapon that Professor Fieser had developed was reshaping strategic planning at the highest levels. But Tinian was merely the proving ground. The true test would come at Iwo Jima, an 8-square-mile volcanic island that Japanese forces had spent a year transforming into the most heavily fortified position in military history. Lieutenant General Tadamichi Kuribayashi, commanding the defense, had studied American tactics exhaustively. He understood American reliance on firepower superiority. He had analyzed previous island battles and identified every mistake Japanese commanders had made. His defensive plan was revolutionary: no banzai charges, no wasted lives in suicidal counterattacks. Every man would fight from prepared positions until death. Every yard would cost American blood. Kuribayashi's 21,000 troops had excavated 11 miles of tunnels through solid volcanic rock. The passages connected 1,500 underground rooms, creating a subterranean fortress that could withstand any bombardment. Multiple entrances and exits ensured defenders could move unseen between positions. Ventilation systems provided air to the deepest chambers. Underground hospitals, command centers, and supply depots made the garrison self-sufficient. Kuribayashi had created a fortress that existed more below ground than above it. The assault began on February 19th, 1945. Marines of the 3rd, 4th, and 5th Divisions hit the beaches, expecting the heaviest resistance of the war. They got it, but not in ways Kuribayashi had planned. Among the assault waves were 8 flame tanks from the 2nd Armoured Amphibian Battalion, specially modified Shermans that had been waterproofed for amphibious landing. These vehicles represented the cutting edge of American tactical innovation, combining armor protection, mobility, and the devastating power of napalm projection. They came ashore on the second day, after engineers had cleared beach obstacles and established routes off the landing zones. Their impact was immediate and profound. Japanese pillboxes that had stopped entire companies were neutralized by single flame tank attacks. The tanks would approach to within 50 yards, their thick armor shrugging off machine gun fire and small-caliber anti-tank weapons. Then the flamethrower would erupt, sending a torrent of burning gel through firing slits and ventilation openings. The concrete structures that had seemed invincible became death traps. Temperatures inside exceeded those of industrial furnaces. Steel reinforcement bars melted. The concrete itself began to crack and spall from thermal shock. Defenders had seconds to flee or die, and fleeing meant emerging into machine gun fire from supporting infantry. Corporal Herschel Woody Williams became the embodiment of infantry flamethrower tactics on Iwo Jima. His actions on February 23rd demonstrated both the weapon's devastating effectiveness and the extraordinary courage required to deploy it. Williams and his squad had been tasked with clearing a complex of 7 interconnected pillboxes that commanded the approaches to the second airfield. Conventional assault had failed repeatedly. Artillery had barely scratched the concrete. Naval gunfire couldn't reach the reverse slope positions. The Marines were stuck, taking casualties from an enemy they couldn't effectively engage. Williams volunteered to take his flamethrower forward. The 70-pound weapon made him an obvious target. Japanese gunners had learned to prioritize flamethrower operators, knowing that eliminating them removed the greatest threat to fortified positions. Williams crawled forward through volcanic ash and debris, bullets kicking up black sand around him. His approach to the first pillbox took 20 minutes of slow, careful movement. At 10 yards, close enough to see the machine gun barrel tracking toward him, he triggered the flamethrower. The stream of burning napalm shot through the firing slit with surgical precision. Inside the pillbox, hell erupted. The gel splashed against the rear wall and spread, coating everything. The temperature rose from tropical warmth to blast furnace intensity in seconds. The machine gun crew had no chance. The weapon they'd been operating melted. Their ammunition cooked off. The concrete walls that had protected them became an oven. Williams moved to the second position, then the third. At the fourth pillbox, he noticed something the reconnaissance reports had missed: a ventilation shaft, barely 6 inches in diameter, protruding from the volcanic rock. He aimed the flamethrower nozzle directly at the opening and fired. The napalm flowed down the shaft like liquid death, spreading through the underground passages connecting multiple defensive positions. Japanese soldiers emerged from cave openings 50 yards away, their bodies wrapped in flames that wouldn't extinguish. Some tried rolling in the volcanic sand, others ran toward the ocean. A few attempted to surrender, but the flames consuming them made coherent action impossible. Within 4 hours, Williams had neutralized 7 major fortifications. Positions that had stopped an entire regiment were cleared by one man with a flamethrower. His actions earned him the Medal of Honor, but more importantly, they demonstrated that even Kuribayashi's fortress could be broken. The general had prepared for conventional warfare. He had not anticipated a weapon that turned his greatest strength into fatal vulnerability. The deeper his troops dug, the more effectively napalm could trap them. The more interconnected his tunnel systems, the more thoroughly flames could spread through them. Every defensive advantage became a liability when facing an enemy armed with flowing fire. The battle for Iwo Jima lasted 36 days and cost nearly 7,000 American lives, but casualty projections had estimated 3 times that number. The difference was napalm. Every Marine officer who filed after-action reports noted the weapon's decisive impact. Flame tanks had eliminated fortifications that would have required days of costly frontal assault. Infantry flamethrowers had cleared caves and bunkers that artillery couldn't touch. The 8 flame tanks on Iwo Jima consumed 10,000 gallons of napalm daily. Support crews worked continuously to keep them fueled and operational. Navy Seabees landed under fire to establish forward refueling points. Chemical warfare service specialists maintained the equipment despite constant shelling. The entire logistical system that had been built over 2 years of development and production proved its worth on that volcanic island. By March 26th, when Iwo Jima was declared secure, the lesson was clear. Japanese fortifications, no matter how elaborate or well defended, could not withstand American napalm attacks. The age of static defense was ending, destroyed by a Harvard professor's rejected formula. Okinawa would be the final and largest test. The island, just 350 miles from mainland Japan, represented the last step before invasion of the home islands. Its defense was entrusted to Lieutenant General Mitsuru Ushijima, who commanded over 100,000 troops and had learned from Kuribayashi's experience. Ushijima knew flame weapons were coming. His defensive preparations included countermeasures specifically designed to mitigate napalm effectiveness. Water reservoirs were installed in cave systems. Fire breaks were constructed in underground passages. Troops were issued crude protective equipment, wet cloths that could be wrapped around faces to filter smoke and heat. None of it worked. The 7th 113th Tank Battalion arrived on Okinawa entirely converted to flame tanks, 54 Sherman tanks equipped with the improved Ronson flamethrower system, capable of projecting napalm 60 to 80 yards with devastating accuracy. These vehicles represented 3 years of development and refinement. They were more reliable than early models, more powerful, more efficient. The crews were veterans who had trained specifically for flame tank operations and understood the weapon's capabilities and limitations intimately. The battle for Wana Ridge demonstrated the evolution of combined arms tactics incorporating napalm. Japanese defenders had created interlocking fortifications on reverse slopes where conventional fire support couldn't reach them. Marines of the 1st Division spent 3 days attempting to advance 100 yards, suffering horrific casualties for negligible gain. On May 14th, Marine officers implemented an innovative solution. They couldn't get flame tanks to the reverse slope positions, but they could get napalm there. Engineer units hauled 55-gallon drums of jellied fuel to the ridgetop under cover of darkness. At dawn, riflemen punctured the drums with armor-piercing rounds. The napalm flowed down the hillside like a Sios, burning river, seeking out every crevice and opening. White phosphorus grenades ignited the flowing gel. The entire reverse slope became an inferno. Japanese soldiers emerged from positions that reconnaissance hadn't even identified, their bodies and uniforms aflame. The defensive line that had held for 3 days collapsed in 3 hours. Ushijima's carefully prepared positions couldn't withstand tactics that combined American technological superiority with tactical innovation. Every defensive measure he'd implemented was overcome by some variation of napalm deployment. The civilian cost on Okinawa revealed napalm's indiscriminate nature. The island's 450,000 civilians had been instructed by Japanese authorities to take shelter in caves during the battle. Many complied, seeking protection from artillery and aerial bombardment, but caves that offered safety from conventional weapons became death traps when flame tanks approached. Marines attempting to clear civilian-occupied caves faced impossible situations. They would call for occupants to emerge and surrender. Often there was no response, either because civilians were too terrified to move or because Japanese soldiers inside prevented them from leaving. Military necessity then demanded clearing the cave to prevent its use by defenders. The flame tank would advance, warnings would be given in Japanese, and if there was still no response, the flamethrower would fire. Lieutenant John Stevens of the 6th Marine Division documented one such incident near Shuri Castle on May 30th. His unit had discovered a large cave complex containing an estimated 450 civilians. Despite repeated calls for surrender and warnings in Japanese, no one emerged. The decision was made to deploy flame weapons. The psychological trauma for the Marines involved was profound. They understood they were killing civilians, but military protocol and tactical necessity demanded clearing every fortified position. The screaming from inside the cave lasted approximately 5 minutes as oxygen was consumed and temperatures rose beyond survivability. When Marines finally entered hours later, they found mostly women, children, and elderly civilians. The flames had consumed oxygen throughout the cave system. Most had suffocated before burning. Stevens wrote in his report that it was a mercy, though he struggled with that conclusion for the rest of his life. By June 1945, when organized resistance on Okinawa ended, flame weapons had consumed 200,000 gallons of napalm. The statistics were meticulously documented. Underground fortifications cleared, over 4,000. Japanese defensive positions neutralized, uncounted thousands. Estimated civilian casualties from flame weapons, at least 20,000, though exact figures remain disputed. The weapon developed to save American lives had proven devastatingly indiscriminate. Professor Fieser's hope that napalm would be used wisely had been overtaken by the brutal calculus of total war. Military necessity trumped humanitarian considerations. Tactical effectiveness outweighed moral qualms. The weapon worked, and in warfare, that was the only metric that mattered. As Okinawa's caves were sealed and its fortifications documented, military planners were already preparing for the invasion of Japan itself. Operation Downfall would be the largest amphibious assault in history. Intelligence estimates suggested Japanese defensive preparations on Kyushu exceeded anything seen on previous islands. 10,000 caves, 5,000 concrete bunkers, elaborate underground networks connecting defensive positions across the island. American casualties were projected to exceed 1 million. The solution was more napalm. Production was ramped to unprecedented levels. Plans called for 75 flame tank battalions, over 4,000 specialized vehicles. Every rifle company would have organic flamethrower squads. Chemical warfare service units would stockpile 5 million gallons of jellied fuel at forward bases. The entire industrial and military capacity of America was being mobilized to produce and deploy incendiary weapons at a scale that defied comprehension. But the invasion never came. On August 6, 1945, an atomic bomb destroyed Hiroshima. 3 days later, Nagasaki was similarly annihilated. Japan surrendered on August 15th. The war ended, and with it, the largest deployment of napalm weapons came to a close. The final statistics were sobering. Between 1942 and 1945, American factories had produced over 40,000 tons of napalm. The weapon had been deployed across every major Pacific battle from Tinian forward. It had eliminated over 40,000 Japanese fortified positions. It had killed an estimated 300,000 enemy combatants and an unknown number of civilians. And it had been developed by a Harvard chemistry professor who had initially opposed weapons research, who had hoped his creation would be used wisely, who had believed moral considerations would limit application. The war ended, but the questions Professor Fieser's invention raised would burn on for generations. Was the weapon's effectiveness worth its indiscriminate nature? Did military necessity justify civilian casualties? Could technology be created for limited purposes and somehow contained from broader application? The cave systems on Iwo Jima still show scorch marks from flame attacks 8 decades later. Okinawa's sealed caves contain the remains of those who chose death over surrender to flames. The weapon that had been rejected as impractical in November 1941 had reshaped warfare and left scars that time could not erase. Fieser returned to Harvard after the war, awarded the Medal for Merit for his contributions. He resumed his research into blood coagulation and vitamin synthesis, work that would save lives rather than end them. But the shadow of napalm followed him until his death in 1977, a reminder that scientific achievement can never be separated from moral consequence, that innovation serves the purposes of those who deploy it, and that the chemistry of destruction, once unleashed, cannot be recalled. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell, so you don't miss any upload from us.